Last time we learned a ton about ratios, proportions, and something called the geometric mean. This time we're going to focus just on proportions because we'll be using proportions for the rest of this unit. I think you probably all believe that this proportion is true. 1 to 2 is equal to 4 to 8, or 1/2 equals 4/8. That's a true proportion because those two ratios, those two fractions, are equal. But there's actually a lot of different ways that we could use those same numbers to set up more true proportions, and that's talking about the proportion properties, which I've given names to them. The first one I call the reciprocal property. The reciprocal is where you just flip upside down that fraction, so 2 to 1 should be equal to 8 to 4. And that checks out. Those are both 2 over 1. Another way you can check is by cross multiplying. 2 times 4 equals 1 times 8. The next way I'm going to rearrange using this property, I call it tops and bottoms. If we look at the tops, or the numerators, the 1 and the 4, what if we compare those in a ratio, 1 to 4? And then compare the denominators, 2 to 8. Well, crazy, those are equal to each other. 1 to 4 is equal to 2 to 8. 1 times 8 equals 2 times 4. So that's another true proportion based on those same numbers. This last one is kind of the weird one. It's called add the denominator, at least that's what I call it. The denominator being the bottom number. So what if I took the top and I added the denominator? And on this other one, I added its denominator. That would give me the ratio 3 to 2 for the first one, and the ratio 12 to 8 for the second one, which are equal to each other. 3 times 8 equals 12 times 2. But this should sound really sketchy to you. Since when? Who's your algebra teacher? Since when can I add different numbers to both sides and come out with a true equation? That should really bother you. Why does that work? Spoiler alert, 1/2 plus 2 over 2. That gives me 3 over 2 with that common denominator. What about the other side? 4/8 plus 8 over 8. That gives me 12 over 8. So it wasn't that I was adding a 2 to one side and an 8 to the other side. I was adding 2 over 2 to one side and 8 over 8 to the other side. I was adding 1 to both sides. Both of those fractions are just a 1. So what looks like an illegal move at first is totally based in algebra. I call it add the denominator. Again, we just take whatever's on the bottom and add it up to that numerator. I just want to practice those 3 properties on this little example. We have 2 triangles, and it turns out that their side lengths are proportional. The ratio of AC to DF is equal to the ratio of BC to EF. And I could solve that to figure out how long segment EF is. But I want to practice those 3 properties of proportions. That first one, remember, I called it the reciprocal property, where I just flip those fractions upside down. That proportion should be just as true as the original. The second one, I call it tops and bottoms. If I take the 12 and the 9 and make that a ratio, that should be equal to the 18 to x ratio. And then the third property, that kind of weird one, where I take the 18 and add it on this one, and the x and add it on this one. 12 plus 18 gives me a numerator of 30 over 18. And the other side, I would have to just write it as 9 plus x. And I keep that denominator the same. It's just the numerators that get added to. I'm going to do a little speed algebra and solve all 4 of these. Now I'm pretty sure that the length of EF must be 13.5. The point is, you can set up these proportions a lot of different ways and get the correct answer, as long as you're comparing like things to like things. For example, on proportion 2, I was comparing the 12 with the 9. And on the other side, I compared the 18 with the x in that order. So I'm comparing like things, which makes it a true proportion. Let's try this diagram. It says that this length JL is to LH as JK is to KG. those ratios are equal. We're going to find JH and JL. So JL over LH. Well, LH is definitely 2. They haven't labeled JL. And JK over KG. JK is 15 and KG is 5. What should we call JL? I was going to say X, but X is actually the length of JH. So if the whole length is considered X, what is 2 shorter than X? That's what I would call this, whatever is 2 shorter than X. Turns out that is X minus 2. So I can call the length of JL X minus 2. Again, that's because that entire length is X, but 2 of it is already used up on this bottom piece. So X minus 2 would be the length of JL. Let's get to the solving. We'll do our cross multiplication. Remember to use those parentheses on problems like this. If we're taking X minus 2 times 5, you're going to have to use the distributive property. X times 5 is 5x. 2 times 5 is 10. Add 10. Divide by 5. And I get x equals 8. Remember that x was the length of JH. We were also supposed to find the length of JL. JL was the x minus 2, so 8 minus 2 is 6. And I think that makes sense. If this was a 6, then the entire thing would be 8. And 6 to 2 is equal to 15 to 5. Those are both equal to 3 to 1. Have you ever been to Knoxville, Tennessee? Their big landmark is called the Sun Sphere, and you can buy little toy models of it. It says the actual building is 266 feet tall, and your model is 20 inches tall. The diameter of the dome on your scale model is about 5.6 inches. What's the diameter of the actual Sun Sphere dome? Well, remember that scale models are built according to ratios. They should be proportional to each other. So if the height of this model is 20 inches, and the actual building is 266 feet tall, we can use that. The diameter on our model was 5.6 inches, and we are trying to figure out the diameter of the actual building. It turns out that we don't even have to convert anything inches to feet here, because if I just compare inches to inches and feet to feet, I should be able to solve this proportion where my answer is in feet. So what is the diameter of the actual dome? Let's set that up. We could compare model to actual. You could go actual to model, as long as you're consistent on both sides. So for the height, the model is 20 inches tall, and the actual building is 266 feet tall. So we've got inches over feet. That doesn't bother me as long as I keep it inches over feet on the other side. Let's talk diameter. 5.6 inches is the diameter of the model, and I am looking for the actual diameter, and that will be in feet. We'll do our cross multiplying. So it looks like the actual building has a diameter of about 75 feet. If you picked up that model and looked at the bottom, it would give you the scale factor of that model. How many times as tall as your model is the actual building? What is the scale or the scale factor? Well, this time we are just talking about a ratio. And if we're going model to actual, this time we do have to think about our units. That was in inches and this was in feet. So if I want to simplify that ratio, I do need to do some conversions. Again, I like to take the larger of the two units and convert that. That way I don't have to deal with decimals. Now that I have those both in inches, I can ditch the units completely, as any good ratio does. And if I reduce that fraction, I can divide them both by 4. I get 5 on the top and 798 on the bottom. And you could consider that the scale. For every 5 inches on the model, I should get 798 inches on the actual building. Now, usually the ratio is written on a model as 1 to something. So if I take the top and divide by 5, and the bottom and divide by 5, that gives you another equivalent ratio, and that's probably more likely to be printed on the bottom of that thing. Remember when we looked at that car, it had the ratio written like this. And even with rounding, I bet it's more of a 1 to 160 scale model. So that's my ratio. If I were to actually say what is the scale factor, I'm looking at what is the multiplier going from the model to the actual. So that 159.6 is often called the scale factor. It just talks about what the multiplier is to go from small to large when you're talking about length.